Hello and welcome back to my channel. In this episode we are going to have our first look at dome ports. How they work, what their strong points are, what their weak points are, and how to set them up properly and what lenses they work best with. Dome ports are commonly associated with wide-angle lenses, but as I showed in the previous episode, all lenses benefit from using a dome port instead of a flat port. Speaking of wide-angle lenses, there is something about wide-angle lenses that I have to make clear before we start. I am surprised by how many people think that a fisheye lens is just a very wide-angle lens. They think that there is no fundamental difference between fisheye lenses and other wide-angle lenses. This is false. A fisheye lens is a very different beast from all other lenses. This is a photo taken with a wide-angle lens. And this is a photo taken with a fisheye lens. Apart from the fact that the fisheye lens is wider, you can see that all straight lines will remain straight lines in a wide-angle shot. With a fisheye lens, only straight lines going through the center of the image will remain straight. All others will show massive barrel distortion. Barrel distortion is usually not something we want in our photos. But with fisheye lenses, this distortion is not a bug. It's a feature. It allows you to reach a 180 degrees field of vision from one corner to the opposite corner. For a normal wide-angle lens, also called a rectilinear lens, a field of vision of 180 degrees would be impossible to achieve. It would require a focal length of 0 millimeters. Now, a lens does not need to have a field of vision of 180 degrees to be called a fisheye lens. It is the distortion that makes a fisheye lens, not the angle of view. Here you see two photos made with an APS-C camera. The one on the left, made with a 10mm rectilinear wide-angle lens. The one on the right, made with a 16mm full-frame fisheye lens. Even though the one on the left is wider, it's the one on the right that, through its distortion, reveals itself to be a fisheye lens. This distinction between rectilinear wide-angle lenses and fisheye lenses will become very important in the second episode on dome ports, because, as we shall see, fisheye lenses perform much better behind dome ports than rectilinear wide-angle lenses do. From now on, I will drop the qualifier rectilinear and call rectilinear wide-angle lenses just wide-angle lenses. This is a good place to introduce you to a very simple mnemonic device to let you understand the relationship between sensor size, focal length, and field of view. Think of a simple T-shape. If the length of the horizontal line is your sensor size, and the length of the vertical line is your focal length, then this is the angle that your lens can see, your field of vision, or FOV. The formula is field of vision is 2 times the arctangus of S divided by 2 times F, where S is sensor size and F is focal length. You can plug in different dimensions of your sensor. Let's take a full-frame camera with a 35mm lens like this Sony RX1. A full-frame sensor is 24mm high. So with a 35mm lens, that would give you a vertical field of vision of 37.9 degrees. A full-frame sensor is 36mm wide, so with a 35mm lens, that would give you a horizontal field of view of 54.4 degrees. Pythagoras tells us that a full-frame sensor has a diagonal equal to the square root of 36 times 36 plus 24 times 24. This is about 43.3 millimeter. So with a 35mm lens, that would give you a diagonal field of view of 63.4 degrees. If trigonometry is not your thing, you can always draw it out on a piece of paper and measure it. You can now easily see why I stated earlier that for a rectilinear wide-angle lens, a 180 degrees field of view would require a focal length of 0 mm. This mnemonic device does not, I repeat, does not work for fisheye lenses. Now that we have all that cleared up, we can return to today's topic, dome ports. As we have seen in the previous episode, light entering the inside of your underwater housing through a flat port under an angle to the normal will produce color dispersion. This in turn leads to color fringing or chromatic aberration. The only way to prevent this from happening is by using a port that will ensure that all light rays reaching your lens have entered the air at the right angles to the port. The only shape that would achieve this is a dome port, a glass or acrylic segment of a sphere. For our further discussion, I will introduce two concepts that are crucial to understanding how to align the dome port correctly with your lens. The first is the optical center of a lens. As light rays travel through the lens and through the aperture, they bend away from the center line of the lens like you see here. The optical center of the lens is where these light rays would have met if they had traveled in a straight line, like this. You can think of this as the camera's point of view. This is where you would have to put the pupil of your eye to get the exact same view as your camera. As you can see, this optical center is somewhere in front of the aperture. The second concept is the center of curvature of the dome port. This one is easy. This is where all the normals to the surface of the dome port meet. Or you could also say, it is the center of the sphere that the dome port is a segment of. As you can see in this case, the center of curvature of the dome is behind the optical center of the lens. To ensure that no refraction occurs, one must position the dome port in such a way that the center of curvature of the dome port coincides as well as possible with the optical center of the lens. So we are going to need to extend the dome forwards with one or more extension rings. As it turns out, there is an easy way to check visually if your lens and dome port are properly aligned. So how do you do it? We have to be able to see where the optical center of the lens and the center of curvature of the dome are. First, the optical center of the lens. That is where your aperture appears to be. Not where it actually is, but where you see it. The aperture always appears to be somewhere in front of its actual position. So in the case of this Sony RX1, the optical center is here. Good. We are halfway there. Now for the center of curvature. How can you tell where the center of curvature is when you look at the dome? What would you see reflecting in that part of the dome? The line running from your eye to the center of curvature intersects the dome at right angles. That means that what your eye sees reflecting in that little part of the dome is the eye itself. Of course, you must close one eye for this to work. There you have it. If a dome port is perfectly aligned with your lens, the reflection of your eye will coincide with the apparent position of the aperture. Now, it may take some twisting and turning before you find a position where you can actually see the aperture and the reflection of your eye at the same time. I will demonstrate all this, but instead of my eye, I will use a camera so I can capture the images. In this first image, you see a dome port on a housing with a camera and a wide-angle lens inside. If we zoom in a bit, you can see the aperture. So the optical center is here. To the right of that, you can see the reflection of the camera that took this picture. So the center of curvature is here. Clearly, this dome port is not well aligned with the lens. So we add an extension ring of 30 millimeters. And now our center of curvature is here. Much better, but not quite there yet. So I add a 17 millimeter extension ring. The center of curvature is now here, a little bit in front of the optical center, but very close. Unfortunately, there is now some vignetting occurring at the widest zoom setting. So unless I was sure I was not going to use the widest zoom setting, I would opt for the 30 millimeter extension ring only. Not perfect, but a huge improvement over no extension ring. Better would be to combine the 17 millimeter with a 20 millimeter extension ring. I now want to talk about aligning rectangular fisheye lenses with a dome port. Remember how I said that the optical center of a lens is where light rays going through the aperture of the lens would meet if they had not changed direction? Well, for a fisheye lens with a field of view of 180 degrees, that leads to a rather extreme situation. For light rays coming in at 90 degrees to go through the aperture, they must do some extreme refracting, as we can see here. To find the optical center of this fisheye lens, we have to see where these light rays would intersect if they were not refracting. That would be here. So the optical center of a fisheye lens is very close to the front of the lens. In fact, it is a short distance in front of the metal parts that hold the lens elements. You should also remember that I said that the optical center is where the aperture appears to be. This leads to a counterintuitive conclusion. We should be able to see the aperture of a fisheye lens when we look at it perpendicular to the lens axis. In other words, we should be able to see the aperture when we look at the lens from the side. Can we really? Let's check it out. Here we look at the front of a fisheye lens. Now keep your eye on the aperture as I start turning it sideways. Well, look at that. You can actually see the aperture from this angle. Back to aligning our dome port with the fisheye lens. To align our dome port with the fisheye lens, we have to move the base plate forward to where the corner light rays coming in at 90 degrees can still reach the lens. From there, an ideal dome would be a hemisphere centered on the optical center. Unfortunately, a full hemisphere dome port is extremely difficult to make. That is why we have to settle for an almost full hemisphere that has its center of curvature a bit behind the optical center. In real life, it is almost impossible to align the base plate of the dome port so close to the front of the lens. Housing manufacturers only produce extension rings at discrete lengths, and it is rare for you to get as close as we see here. In fact, you may end up with the base plate slightly in front of this position, leading to vignetting, as we see here. You could try to crop the image, like this, which is not such a great idea if you are shooting video. A second option that you can use on photos, and I would always recommend for video, is to push back on some of the barrel distortion with a lens correction, like this. You may actually prefer this look even without vignetting occurring. Until now, I have treated the optical centers of lenses as if they are at a fixed place inside of the lens. For prime lenses, this is mostly true, but it is not true for zoom lenses. So what zoom lenses are suitable for use behind the dome port? Those lenses where the optical center moves as little as possible as you zoom in and out. In other words, those lenses with the lowest apparent movement of the aperture as you zoom in and out. Let's test a wide-angle zoom and a standard zoom. We start with this wide-angle zoom lens, the Sony 10 to 20mm f4G lens. Here we see the optical center at 10mm. And here we see the optical center at 20mm. Again at 10mm and at 20mm. As you can see, the optical center doesn't move very much. I would say around 5 to 6mm. It is typical for wide-angle zoom lenses that their optical centers do not travel too much during zooming. Another desirable thing that you can see with this lens: the optical center moves forward as you zoom in and backwards as you zoom out. That is something you want to see in a zoom lens behind a dome port. You align the dome port with the lens at its widest zoom setting, and as you zoom in, you want the optical center to move forward towards the dome port. Now for a standard zoom lens, it becomes tricky to see the movement of the aperture, as it becomes hard to keep a visual on the aperture at enough of an angle as you zoom in and out. The whole lens gets shorter and longer, so it is hard to judge how much you see the aperture itself move back and forth. Let's try this Sigma 18 to 50mm f2.8. This is the optical center at 18mm, and this is the optical center at 50mm. Again at 18mm and at 50mm. Even at this angle, we can see that the optical center travels further back and forth with this lens than with the wide-angle zoom. But you may also have noticed that the optical center is traveling in the wrong direction. It moves back as we zoom in. This is true for all the standard zooms that I have tried. But please let me know in the comments below if you know of a standard zoom where the aperture seems to move forward as you go from wide to narrow. If the optical center travels in the right direction, that is, forward as you zoom from wide to narrow, I would advise that you align your dome at the widest zoom setting. If the optical center travels in the wrong direction, I would advise to align your dome at an in-between zoom setting. Lastly, as we did with the episode about flat ports, I will discuss what difference the material of the dome port makes. What's the difference between a glass dome port and an acrylic dome port? Optically, the difference between glass and acrylic dome ports are negligible. The only optical advantage of a glass dome port that I can think of, as with flat ports, is that glass can be coated against reflections. I have used this Nauticum acrylic dome port in the past, but these days I use this Zen Underwater glass dome port in combination with extension rings. I cannot say that the Zen Underwater is optically better, and I don't see any differences in the optical quality of the photos I have taken with these two ports. The reason I switched to the Zen Underwater dome port are all of a practical nature. They are: a glass dome is far less likely to scratch than an acrylic dome. The weight distribution. The Nauticum acrylic dome port is very buoyant at the front end, which is annoying as hell and makes your wrist tired and your video shaky. The weight distribution of the glass Zen Underwater dome port is excellent. Not only because glass is much heavier than acrylic, but the whole aluminum base plate of the dome port is thicker and heavier. I am more flexible with the positioning of the dome port because I can put all kinds of combination of extension rings between my housing and this short dome port. With the Nauticum acrylic dome port, I cannot bring the dome any closer to the camera. Ergonomics. This Zen Underwater dome is much easier to travel with because inside the limited space of a pelly case, you can pack the combination of a very short dome port and separate extension rings much more tightly than the awkward shape of this Nauticum dome port. One thing that does have a huge effect on the optical quality of a dome port is the radius of the dome. Not the diameter of the dome, but the radius, the distance from the center of the curvature to the dome port. The bigger the radius, the better. Why that is will be made clear in the next episode. I think this is a good time to end this first episode on dome ports. To summarize this episode, rectilinear wide-angle lenses and fisheye lenses are very different from each other. A fisheye lens is characterized by extreme barrel distortion, not by its angle of view. Underwater, dome ports are a must for wide-angle and fisheye lenses, but they will benefit the optical performance of all lenses. To eliminate all color diffraction, the optical center of the lens should be as close to or in the same spot as the center of curvature of the dome. If the dome port is perfectly aligned with the lens, the reflection of your eye will coincide with where you see the aperture of the lens. The best zoom lenses for use behind a dome port will show as little travel of the optical center when zooming in and out as possible. It is also preferable if the optical center moves forward when you zoom in. Wide-angle zoom lenses have less travel of the optical center than standard zoom lenses. Balance and buoyancy underwater and scratch resistance are reasons to go for a glass dome port over an acrylic dome port, not the optical quality. Well, that brings us to the end of this first episode on dome ports. I hope it has taught you something of value. Please join us for the next episode, where we will explore the issue of dome ports and field curvature. If you like what I'm doing on this channel, please help me out by liking and subscribing. See you next time. Bye bye.